Grade 12 Physics, Energy Momentum Note number 4, Simple Harmonic Motion. Simple harmonic motion is an extension of conservation of energy, where we have motion that basically repeats itself, and that's why it's called harmonic. So an example might be a pendulum moving forward, backwards. That's motion that repeats itself, so we could call that harmonic. The example that we're going to examine here is, let's say we have a mass on the end of a spring hung from a ceiling. If we were to hold that mass up and release it, it would bob up and down, and we could call that simple harmonic motion. So when that happens, eventually it'll slow down and come to a stop. So there's two different features we need to recognize when we solve these problems. As a rule of thumb, after all motion is done and the system has come to a complete stop, that is the only time we're going to use force analysis on the object. We know that when it's at rest, forces are balanced. But when it's still in motion, we can use energy analysis, where kinetic energy equals spring potential, and we might have to factor in a gravitational potential. So let's use example 1 here. So a system set up like that diagram above, where mass is 0.75 kilograms when released. When it's released, the maximum depth of that first drop is going to be 0.24 meters. So that's the information given here to start. Let's say after a period of time it's come to a complete stop. And the rest position, the extension of that spring at the rest position is going to be 0.12 meters. Here, let's calculate the K value of that spring. So when it's at rest, we know that our forces are balanced. Fg must be equal to the force on the spring. So we can set them equal. So Kx equals mg. And here we can solve for K, which ends up being 61.25 newtons per meter. Now on part B, let's try and figure out what's the maximum amount of energy in that spring. So this is when we need to consider, well, when is the spring stretched the most? That's from the original question. The maximum extension would be that first drop, which would be 0.24 meters. So here we're just going to use that spring equation, where we have 1/2 kx squared. We put our numbers in, where x is 0.24, and we get 1.76 joules. Last portion here is, what is the velocity when that spring is stretching and it's stretched to a point of 0.18 meters on that first drop? So here we're going to use, it's in motion, so we're going to use energy analysis. Energy initially equals energy finally. We know the total energy in the system is 1.76 joules, so let's just use that as our initial energy. At the 0.18 meter mark, we're going to have gravitational potential, we're going to have kinetic and spring energy, so we need all three of those terms. If we start putting in our numbers, G is 9.8. The height at that point is just going to be height from our lowest point, so we need to subtract 1/8 from 0.24. Our stretching of the spring is 0.18, and I apologize, it's cut off. I'll fix that later. We're going to put our velocity, or we're going to solve for our velocity there at the end. We find it eventually, it's 0.94 meters per second. Now, if we're looking at harmonic motion, something that repeats itself, that means we're going to be able to calculate a frequency or a period of the system. Remember, frequency is how many cycles we can get in a second, versus the period is the time taken to do one of those cycles. Let's consider a rotating wheel, similar to the diagram in your note, where we have a peg at some point on that wheel. The wheel would be turning, it has some radius r. If we align it so that we're standing beside the wheel, all we're going to see is the peg go up and down, up and down. So let's consider that view of this motion for our derivation. Here, because that peg we know is going in a circle, we can use circular motion equation where the acceleration will be v squared over r. The velocity of that peg will just be a distance over time, where the distance would be the circumference of the wheel. So it would be 2 pi r divided by the time taken to do one cycle, which essentially is the period. So let's put our value here for v into that original acceleration equation. Expand that exponent, we get that as our feature, and let's rearrange for our period. So we get t squared equals 4 pi squared r over a squared. Let's get rid of that square on the t, and now we have t equals 2 pi times the root of the radius divided by acceleration. The other part of the diagram at the top has a mass on the end of a spring. So the acceleration of that mass, we know that there's F equals ma, and we have to deal with a spring, which is F equals kx. So here, because it's accelerating, we can use kx equals ma, rearrange for that a, and actually rearrange a little bit more to get x divided by a, which is equal to m over k. So here, x, that's the stretch, which is equal to r. We can sub that into our original equation and now get a period of that motion, which is equal to 2 pi times the root of the mass on the end of that spring divided by the spring constant. This is an equation we can use to find the period of that oscillating spring system. So let's say we have simple harmonic motion with a 2.5 kilogram mass on the end of a spring with a constant of 125 newtons per meter. Let's try and calculate the frequency of this system. So to do that, first we need to calculate the period. So let's use our new formula, 2 pi m over k. We here find that the period to do one oscillation would be 0.89 seconds. Let's remember frequency is the inverse of period, so we just divide it by itself and we get our final answer.